A very good morning to all the distinguished speakers and scholarly delegates connected with us on this virtual platform. I'm highly honored and it gives me an immense pleasure to extend a warm welcome to all of you on behalf of Department of Mathematics, Gujarat University on this second day of Digital International Conference on Advances in Computational Methods 2020.
Hello everyone. I hope you all must have enjoyed and enlightened yourselves with the knowledge from yesterday's lectures. Today we have among us Mr. Charlie, Professor Gaurav Srivastava, Dr. Prashant, and Professor Gaurav Dwivedi. I request Milan to introduce our first speaker of the day.
Thank you, Pratik. So we start this session with our first speaker, Mr. Charlie Day. Mr. Charlie is the Director of Training and Professional Development at Texas Advanced Computing Center, University of Texas, Austin, USA. He holds a bachelor's degree concentrating in computer science and biology from Eastern Illinois University and certifications in 3D programming and visualization. He organized, hosted, and assisted in designing of curriculums of TACC's Summer Institute series, such as Parallel Foundations, designing and administering large-scale systems, machine learning, and data analytics, and so on. He is one of the technology expert of Fortran, C, C++, Python, R, OpenMP, MPI, and Jupyter notebooks. His papers have appeared in a number of high-impact journals such as Computer and Mathematics with Applications, International Journal of Computer Mathematics, and many more. His broad research interest is in bioinformatics, numerical analysis, object-oriented programming, parallel programming, cloud computing, scientific visualization, and computer animation. He was also a member of specialized application development team at the University of Illinois and has been a contracted research consultant for NASA Ames Research Center, study computational immunology and bioinformatics. He is going to talk today on an introduction to data science using Jupyter notebooks and Python. Sir, we are fortunate to have you on this platform. So over to you.
Hey, thank you very much, and thank you for that very nice welcome. Thank you, Professor Shah, for inviting me to give this talk. I really actually enjoy giving these kinds of talks. I really like reaching out to the community and knowing and learning what everybody is doing in numerical mathematics and mathematical modeling. So this has been a great conference. Thank you very much for organizing it, and thank you very much for having me. So on that note, I know many of you probably have never heard of TACC or the Texas Advanced Computing Center before, so I was going to take a little bit of time and tell you guys who we are and what we do and how we got to where we are. So everyone, welcome to TACC, though honestly, welcome to my room. I would love to have you guys hosted at TACC at our actual center, but unfortunately with the current times, we make do. So with that, let me get my slides. All right, so TACC, at a quick glance, we're a research center located at the UT Austin. We have about 175 people on staff, 70 PhDs, and about 20 students. There's a photo of all of us here from one of the last Zoom meetings we had as a center. We have about 10,000 users on our systems on about 2,300 or so projects, though honestly, that number is a lot larger. We have 10,000 people who actually use our computers on a command line. We have about 50,000 users on top of that use our scientific gateways to access our systems and get to our data and perform their science. And essentially, that's our mission. Our mission at TACC is to enable discoveries that advance science and society through the application of advanced computing technologies. My personal mission at TACC is to teach scientists how to use our technologies at TACC so they can do better science. Our infrastructure, we have probably 1 billion compute hours per year, probably a little bit more than that. We have over 5 billion files and 50 petabytes of data sitting in on our spinning disks in our shared public data sets. Hundreds of public data sets on top of that. Some of them are actually really cool. One of the public data sets that I recently came across is University of Anchorage in Alaska. They have been tracking whales throughout their migratory patterns throughout the world, and they've been recording their songs at different parts in the ocean at different parts of different times of the year to see how their songs are changing. We have about 10 megawatt data center. We have about 10,000 square feet and approximately 20 or 30 different high performance computing resources for scientists to use. Of those resources, there can be like HPC or high throughput computing, cloud computing. We do the portals and the gateways. And then of course we do what I'm doing, which is consulting, data analysis, code optimization, and training and outreach. So we have this big hierarchy, this ecosystem at TACC, which is taking all of that together and then producing and helping scientists do better science, right? Of that hierarchy, these are some of the machines we have. We have Stampede 2, which is one of our showcase machines. It is number 21 on the top 500 fastest supercomputers in the world. And then we have a bunch of other machines that support it. We have Wrangler, which is our big data-intensive computing machine that does 1 terabytes of data per second is what it can analyze and read through. We have a machine learning system. We have public data sets sitting on spinning disks and then replicated. We have a cloud computing system known as Jetstream that we're using on multiple locations in the US. And then we have some experimental systems. Though I should say these experimental systems and even our production systems, they're all experiments. They're all something that's never been done before that we put together in a very novel way. One of the systems we have is a machine called Chameleon. Chameleon is something, it's a system built for computer science. It is, if you're a computer scientist or a numerical analyst and you have a new numerical algorithm that you have like to test using different hardware components, then Chameleon has a different CPUs, a bunch of different GPUs, different memory segments, and essentially you build a machine and you test your algorithm on it. So all of these experiments that we've been building, all of these machines that we've been building has come to a peak. Well, maybe a peak and maybe even a future peak would be great too. But we call it the computing for our endless frontier. Dan Stanzione, who is our executive director, coined that phrase. The idea was we want to build a machine that is going to be the new tool for scientists to use. And we have this new machine we created called Frontera. And this is the timeline that it took to get to Frontera. Some of the highlights, and I want to point this one out in particular, is in 2007, which was not even 15 years ago, we won our first major award from the National Science Foundation, which was to deploy this machine called Ranger. At the time, Ranger was one of the largest open systems, and it came up at number 4 in the top 500 supercomputers. Ranger was number 4. And this is a picture of Ranger in the bottom corner. And then, of course, we've got new machines. Other machines got retired and so on and so forth until Stampede 2 came around in 2016. And then Frontera came out in 2019. Last year is when we deployed it. We're going to operate it for 5 years. One of the cool phases of Frontera is going to help design Frontera 2. And Frontera 2 is going to have 10 times the capabilities that Frontera has. So Frontera is now the 8th fastest supercomputer in the world. It's number 1 for open science. It is about 35 or 40 petaflops of performance that we get from this machine. And of course, we have everything that we've done in the past. All the machines that we've built and we've learned from have gone into designing and building Frontera. So this is kind of what the overview of the system is. You have different ways of accessing it. The entire system is connected through the high-speed connection. We are going to be connected, or it connects to the commercial cloud as well. And it's got a it's got a subsystem for computing for using machine learning and GPUs as well as the CPUs. Just to give you an idea of how big it is, this is our 1 rack of Frontera nodes There's about 90 nodes in each rack. This is one of our system admins. He is 6 feet 4 inches tall, so he's a really, really, really tall guy. He has to get on his tippy toes to get to the top of the machine. But one thing I wanted to point out is Frontera, one rack of Frontera is more powerful than the Ranger supercomputer was that we built not even 15 years ago. Oh, so okay, so where does that take us to? Well, that takes us to this quote from Harvey Davy, who invented electrochemistry in 1812. Essentially what he's saying, for humans to be able to tap into our intellectual powers, we need new tools. And essentially, we're pretty sure he was talking about our machine, because our machine is going to be that tool. Some of the research work that's been done on our machines is, of course, wind farms. We have been doing image classification using machine learning. We've been doing probing space oddities and space junk, so we can map out with NASA what the space junk looks like, what things we have to be concerned about. Then, of course, climate change. The Ross Ice Shelf is something that we're monitoring and we're looking at and keeping data sets on our machines. Something I should say is our boss likes to say supercomputing is the climate change paradox. It is both the solution to and the cause of global warming. And then, of course, brain tumor segmentation, where we're analyzing MRI scans to be able to understand when cancer cells, to early detection of cancer in the brain. And then, of course, things like earthquake forecasting and aftershock forecasting, astronomy, the solar corona predictions. TACC actually played a role in the gravitational wave observations for the first time. Essentially, we increased their runtime by 10 times improvement on that. And then taking that data set and then being able to animate what the gravitational wave actually looks like when you have two neutron stars colliding. And then, of course, weather forecasting as well, using machine learning for cancer detection. And then we're also using machine learning to improve child welfare. So we can target children that need extra care from the state or from DCFS to step in and make sure that the children are being taken care of, well taken care of. And then, of course, this is one of my favorite ones. They're actually using machine learning to do better dance choreography, so prettier dance. So, and of course, luckily you guys are not in Austin right now. Austin is notorious for having, well, I guess in India you have notorious bad traffic as well. In Austin, we have really bad traffic. So we've been taking years and years of traffic cams, using machine learning to identify what are hazards and what is regular traffic and what is people, and being able to understand why Austin traffic is horrible. And actually in the demo, you'll see exactly why Austin traffic is horrible. All right, and of course, we're doing COVID-19 research, of course. We are using social distancing information that we're getting from cellular phones and like Facebook usage to understand where people are and where the hotspots are arising. And Lauren Ansel Myers over here on the left, she came up with this method that then we're using that to graph where the hotspots are in the US for COVID. And she was recently interviewed on CNN for her research work. Okay, so that takes us to our entire cloud, our entire ecosystem. Now, where does that actually put us? Okay, so we are mathematicians. We do mathematical modeling. We do numerical analysis on our data sets, right? So where does that take us? Well, that takes us into data science. All of us are data scientists, really, because we're on Facebook, we're reading the news, we're compiling information, we're analyzing that information, and we're trying to figure out what that information is trying to tell us. So we have to understand, to get there, we have to understand what is data. So I decided to go ahead and hit Google, let's figure out what does Google think data is. All right, so Google, what is data in a computer, statistics, data mining on a phone. All of this is true. And all this is very different as well. So we got to dig into data a little bit more. All right, so data is a set, this is from Wikipedia, data is a set of values of subjects with respect to qualitative or quantitative variables. Okay, so that gives us a little bit more information about what data is. Now, they say that data and information and knowledge is used interchangeably. However, data only becomes information when it's viewed in context or in post-analysis. So essentially, data is meaningless until you understand the context the data came from, and then in post-analysis, when the data actually displays the information that it carries. Okay, so essentially data is everywhere in that case, right? So, and then I always like to think about, where is my data? You know, where is my data sitting at? Well, my data is sitting with Google, of course. My data is sitting with my bank. My data is sitting with Facebook. My data is sitting with YouTube, with my phone company, with my bank, with my credit card company. Everybody has my data set. So why do they want my data? Well, because your data is very, very valuable, right? So what makes it important? So this is where data science comes into play at. So I decided to Google what data science is. And I get data science is, well, different branch of my favorite, overrated, fad, just statistics, not a science. Data science is a team sport. I got to understand that one a little bit more. But essentially, data science, we don't really have a good example of what data science is or a good understanding of what it is. Back to Wikipedia. Data science is a multidisciplinary field that uses scientific methods, processes, algorithms, systems to extract knowledge and information. Okay, so there's that word knowledge again. So we know that data becomes information when it's viewed in context. All right, so now when we analyze it, we are pulling that knowledge and that insight from, when we're using science on it, we're pulling that information out. All right, so those are two key pieces of information we need. Data is valuable. When we understand the context, then it becomes information. And when we apply science to it, that's when it becomes knowledge, or we can extract the knowledge. I like to say that data science is the ability to understand that there is a story inside your data set. So when my father gave his lecture yesterday and he showed you all the graphs, every run he does, there is a story in that data set. The cancer grew, the cancer died, the cancer metastasized, your immune system failed or your immune system rose to the occasion. Different medications stimulated different parts of your immune system to fight the cancer. So there is a story in that data set. It comes to the understanding of, how do we get that story out? That is where science comes into play at. And then these are some stats I just pulled out. I just found these interesting. Applying data science, Southwest was able to save $100 million by reducing the amount of time the airplane sat on the tarmac. But my favorite is the bottom one. We did an analysis at TACC, and we found that if our machines are sitting idle, it's costing us $32,000 per node sitting idle. So you have to make sure that you researchers are using our systems. All right, so data is worth money is what we understood from here. And then, of course, we go into this era of big data, all right? Big data, to get there, we have to have scale, speed, and ubiquity, all right? Essentially, scaling was introduced, or the idea that data was portable came out in the 1890s with punch cards. For those of you on the call who've never seen a punch card before, this is what it looks like. Essentially, punch out different parts, and it's giving us different knowledge base, right? But it was difficult to scale that. You can only scale that so far. So then we have systems like ours, which are built up to be able to scale up your data set, right? So you can have petabytes and petabytes of data sitting and waiting to be analyzed by a supercomputer or using machine learning techniques. Speed, of course, we have to have speed to be able to understand, to move around our data set and compute it and understand it. And then ubiquity, meaning the data's got to be there. It's got to be everywhere, and it's got to be very common for us to be able to use and understand. All right, so to put the science in it, we then look at all the data points that are being collected. We have to understand that the data is there. It exists. We know there's value in it. But what can we learn from that? So this is where the catch comes to play at. You can only understand how important the data is to do good analysis work on it if you understand where the data came from. All right, you have to understand the context of the data, which is why there is so much misinformation that goes out, because people don't understand the data they're looking at, and so they're trying to fit a story that doesn't fit with the data set, and so you have misinformation. All right, so this comes from experimentation. It's the heart of modern data work. I will also go out to say that numerical modeling, mathematical modeling, is the brain behind modern data work. And then that brings us into machine learning, and then we'll do our demo here. So machine learning, everybody thinks that's some sort of magic bullet. Oh, I'm going to learn machine learning, and that will tell me exactly what I need to do to my data set or what I need to do to my variables to get the outcome that I want. All right, all this traffic is around us. I'll use machine learning, and it'll tell me how to build my roads. It doesn't quite work like that. It's not a magic bullet, is what I'm trying to say. So there's different types of machine learning. There's supervised learning. Supervised learning is essentially probably the most well-known branches of data science. It's about predicting an outcome. All right. So essentially, I've done this experiment before, and I know what the outcome of the experiment is. Therefore, I know if I can change my experiment a little bit, I know that I can predict what the next outcome is going to be. Right. So I can use supervised learning to be able to analyze what the outcome is going to happen and get better predictions each time. Basically, taking what's happened in the past and applying it to the future. There's also unsupervised learning. Now, unsupervised learning to me is very, very interesting, because this is where the cancer research work comes into play at, because we are trying to make predictions, not what the outcome is going to be, but understanding what the relationship between my data sets are. So how does the immune system and how does the cancer interact? What is that relationship? That is what we're trying to learn. And that is where unsupervised learning comes into play at. We're looking for relationships or associations that exist within the data set. Then that gives us cleaner data, more understanding of the data. And then, of course, one of the things is, I gave an example, is the new friends on Facebook you might know. It's just basically, how are these data points related? And then the last one in machine learning is reinforcement learning. To me, this is essentially an iterative learning scheme, right? When you see the computers learning how to play video games, they go crazy and they do the same thing over and over and over again, each time getting farther and farther along a set. Imagine this is the toddler learning a game, and he's learning it over and over again to try and get the game better. He's doing it through reinforcement. All right, and then we have the big buzzword, which is artificial intelligence. So artificial intelligence and machine learning, they're related, but machine learning is all about prediction and all about understanding data sets. Artificial intelligence is, we want to know what the human interaction of that data would be. Essentially, what kind of human interaction, and this is intended for the somewhat human or intelligent that carries out those interactions, right? So we want to know what the insight of the data is. Not just what the data is saying, but what the under knowledge is, what the underhand knowledge of that data is, what the insight of the data is. That's where artificial intelligence comes into play at. All right, so in a nutshell, and then we'll move on to our demo here, because I want to make sure you guys have a chance to see this. Data is important. We need to understand what the data is, what the data means, and that is how we find out what the underlying story is. And we have all these different means at our disposal. All right, so let me show you a quick little demo on understanding data set and getting a better, clean picture of what data means, right? So normally I code this out by hand, and I just do this live in front of you because it's actually a lot of fun to do. But there is almost all cities now have an open data set. Austin, Texas has an open, if you go to Austin, Texas, opendata.gov, you'll have lots and lots of open data sets for you to look at. I went ahead and pulled down the traffic data. which is just a comma delimited file. If we look at it, now this is in the Jupyter Notebook, by the way. Jupyter Notebooks are awesome. I love using Jupyter Notebooks. It makes understanding data sets very quickly. All right, so here's a bunch of data, right? And honestly, it's not making much sense to me. It is a bunch of numbers, a bunch of commas, decimal points, some text, and it looks like a timestamp thrown out there, right? So let's analyze this data set. Let's just do some simple analysis on it, understanding the context. So the first thing we're going to do is I'm doing this all in Python, and I'm going to import the libraries. I'm going to import pandas and NumPy. Pandas is a data analysis library for Python. It's very, very powerful, and it's got a lot of cool things you can do with it. NumPy is essentially numerical pi. It gives you all the numerical libraries to do essentially your statistical work on it. And then I'm going to do everything in a plot. So I'm going to hit Shift-Enter and run all those lines. And now using pandas, I'm going to read in that data set. So now the data set has been read in, and I'm going to look at what that data set looks like. So I'm just going to print out df. df is my data frame. And I get some more information on it. Now, if you look, okay, this is a little bit easier to read than just the flat-out raw file. I do see my timestamp. I see an issue, says crash urgent. I see longitude, latitude, an address, and a status, right? Okay, this is kind of cool, because then what we can do is we can take the longitude and the latitude, and we can graph those. I'm hoping everybody's still there. Okay, that looks better. I'm going to go ahead and graph those. All right, using matplotlib, scatter plot, throw all the longitude and latitudes up there, and I get something that looks like that, which is meaningless. All right, obviously there are inconsistencies in the data. This is where maybe we should narrow it down a little bit. So I can say, using pandas, I can ask my data set, only show me where the issue reported is crash urgent. So I'm going to do that. And I'll print what it looks like. So now what I have is I have a bunch of true falses. So I still have the row ID that we saw over here. So we see all these rows. And now it just tells me which ones are crash urgent and which ones are not. So I can narrow my data set down. So okay, that's great. Now our data set's lowered. I'm going to say, all right, now give me a data frame with just where those are true. So now I got this data set called collision. Now these are only where crash urgent is true. All right, so now I narrowed my data set down. I'm only at like 28,000 rows. So let's graph it. All right, so obviously you read ahead. You saw that querying down didn't solve anything. I still have these inconsistencies. Okay, I'm from Austin, Texas, so I understand some the nuances of the data, right? I can see that if I'm just graphing longitude, latitude, I know what the latitude and longitude of Austin, Texas is. So I'm just going to query that. I'm going to do it the same way I did up here, just with the true falses, right? So I'm going to say, give me where the latitude is greater than 30. Give me where the latitude is it's not less than 3. Okay, that's fine. And the same thing with longitude, less than minus 97, and we'll combine all that together, and hopefully we'll get something better to graph at. Hey, it's looking better. Let's modify that just a little bit using matplotlib. I'm going to just make those dots a little smaller. It's coming up, something a little bit more of a clearer picture. Let's make that a little bigger, shall we? Okay, what you're looking at inside here, let me make that a bit bigger in case you can't see it. That is a map of Austin, all right? So essentially, our traffic here is so bad that if I just do traffic accidents, you get an entire map of the entire city. All right, that's fun and great, but the way doing these kind of data queries is kind of annoying, right? Because you have to do all the true falses. There is something called the lambda expression, or essentially what it is, it's an anonymous function. Lambda expressions are useful in machine learning because essentially what you're doing is you're laying out the schematic for a function. You're not defining the function exactly. You're defining what the structure of the function is. Then later you can pass to that function other syntax to make that function more knowledgeable. So in a machine learning algorithm, since you need the system to change with time, you give it a structure of what it is you want to build. And then you pass more relative information to it as it grows. So I created a Lambda function here called dfQuery. I'm going to pass it an X. And in this case, dfQuery is going to return me a new data set on whatever it is I'm looking for. And then I can pass in whatever I want. So here I'm passing in a data frame, dfQuery of crash urgent. And I'm going to put that in df1. And then I'm going to do another data set. I'm calling my same thing, dfQuery, and I'm passing in collision. Same function. It's going to be doing different stuff for me. So now I'm going to define that function. And now I'm going to graph this using matplotlib, just the crash urgents and collisions. And we get this, essentially, map of Austin, Texas. You can tell where the dark blue is. That's downtown. I live right over here in this area where you see all the little red, because there's a couple intersections that happen there that people, and the red light stays red so long, people always fly through it as fast as they can, and they end up causing accidents. This is also very interesting because places we would expect to see accidents happen, we see that accidents don't happen there. Like this road right here, because I understand Austin, is a blind curve going around a hillside, and you can't see on the other side of the hill. When we first looked at that, we thought, you know what, that's probably where accidents happen a lot. But when we looked at the data, accidents happen there. Then we looked at why. Well, a couple things. The road is banked, so cars have to slow down to go around it because it's an inverse bank. And secondly, because it's a blind corner, people slow down for that instinctually. So before, when we came here, we had a bunch of random numbers that we didn't quite understand. We did some analysis to it. We added some context to the data. Then we brought some insight into the data of where we know Austin to be. And then we're able to essentially understand what our data set is telling us, which is essentially telling us there's a lot of car accidents that happen around Austin, Texas. All right. So with that, I wanted to make sure I stayed here so we have enough time for some questions and answers if possible. Are there any questions? I know I went through that really quick. Like I said, I really, there's actually a 2-hour, 3-hour version of this tutorial that we actually go through and we apply some machine learning techniques to the traffic. And then we could say, all right, let's close this road and rerun our data set and just see what happens. And that's where the fun stuff really happens at. But I'll open it up to if there's any questions or anything. I'll be happy to answer them.
Yes, thank you. Thank you very much, sir. Ma'am, is there any question from your side?
Charlie, it was very interesting demonstration of traffic and accidental zones. But as you know, in India, with 130 million population, can this work?
So
Because even roads are very narrow, even highways are very narrow. So can it be done?
If the data is being collected, then yeah. So we use traffic cams here in Austin. So a couple years ago, traffic cameras were used mainly to find people who are speeding or breaking laws. Now we can't use traffic laws because our laws have changed. We can't use traffic cameras to find people breaking the law, but we can use traffic cameras to collect data sets. And that's what we've been doing over the last few years to analyze how traffic is. One thing you can do is using machine learning techniques, and I should have had that video playing. but we can analyze and we can do what we call what if scenarios. We can do predictions. So we can change orientation of roads. So we can say, all right, now this road is going to be a one-way road from 12 o'clock in the afternoon to 5 o'clock in the afternoon. We can go on the computer and say, all right, we're going to make this road one way. And now we can run a unsupervised data analysis on it to see what happens to the traffic outside of those areas. Will it improve? Will it slow things down? Will our traffic accidents go up or will our traffic accidents go down? We don't know. But we have the data to be able to make those kind of predictions for us. And that's where we're trying to head to. At least in this little demonstration, that's where we're trying to head to.
Thank you. Thank you.
We just make sure the data is there and is being collected, and we understand the context. Context is very important. Without context, that's where misinformation comes from.
Because I think misinformation will be much more because we don't follow traffic rules like what you have in Florida or Illinois or Orlando. Okay? So let me see how I can go ahead with. And if needed, I will obviously contact you. My research team will at least contact you.
Yeah, that's my job. That's what I love doing. That's what I do at TACC. So I help scientists better their science. So,
thank you.
Thank you. Thank you for having me. I really appreciate this.
Yeah, thank you very much, sir, for sharing your ideas, which really enrich our existing insight about the data science. Thank you very much, sir.
Charlie, there are questions. First question is, we are BSc students, so how should we proceed further?
If you want to proceed further with machine learning, you feel free to contact me, and I'll put you in touch with people that know far more than I do. Or I have a couple online tutorials using in supervised learning and unsupervised learning, and give you some techniques and some algorithms and some Python libraries that you can, and sample data sets that you can actually use those on as well. Feel free to contact me. My email is right here, charlie@tac.utexas.edu, and I'll be happy to get you in touch with them. Yeah, feel free to. I love listening to you guys, and I get new ideas.
I will share it.
Please do. Thank you.
Yeah, sure. Second one is, should we go for machine learning first or artificial intelligence first?
So machine learning is where I would suggest going first, because AI comes into play after we have an understanding of the data set. Machine learning, data science will give you the data set, and then AI will give you the insight to the data set. So yes, both is where you want to go to.
So both of them actually goes together?
Both go together, machine learning first, and then AI to get the insight.
Yeah. Next question is, can you suggest the project for graduation program?
Project meaning what you want to do for your thesis work?
Yeah. In India, we do have a project for the MSc students. That is in PG course.
So honestly, something that I know that India has been trying to do for a long time is using better land use for agricultural work. All right. So if I were to think of one thing that's going to change the world, is farming and better agriculture. Because our population is going up, we're going to need more food. Can you use there's lots of data sets exist for this. In fact, I think Tata was doing research in agriculture and farming and applying machine learning to it. So they probably have data sets. I'm not sure if they're public or not, but they should have data sets available for you to understand where the farming can go to and how farming can grow and what plants to grow at what times, and have the machine, have an AI be able to tell us that information. That'd be pretty cool. At least that's what I would think would be pretty cool. And of course, Pandemics. If we can understand how pandemics, how coronavirus, in particular coronavirus right now, is flowing from person to person through the air, how long it's existing when it hits the ground, can children take disease from one place to the other, where the hotspots are, the coolest things that Facebook and Apple are doing now with their phones is if you are in a hotspot and you had your phone on you, it's supposed to be able to send you a notification that, hey, you are in a COVID-19 hotspot. Go get yourself checked out. So,
Yeah. Our host is having one question. He is Sagar Panchal, and he is asking: uh, there some laws for AI/ML for how to use data?
honestly, I'm not 100% sure on how to answer that. But if you shoot me an email, I'll be happy to find an answer for you. So I'm not really sure what the loss would be there. That's a good question, though. Oh, the laws. Yeah, I'm not, like I said, I'm not 100% sure. We have our data analysis guys from our big data team at TACC that I work with. I'll ask them. That's a good question. There are a lot of really great algorithms out there. K-means, random forest, and a few others. And there is no magic bullet in which algorithm works best. Honestly, the data scientists I work with, they just have a favorite algorithm they like, and that's the one that they use. I don't think we haven't found a magic bullet that tells you this algorithm for this case. A lot of it is trial and error, right? Reinforcement.
In fact, Sagar, it varies from problem to problem.
Yeah.
So
very much
you can formulate according to rules and regulations which a particular country follows or a particular territory follows.
Yes. Okay? Absolutely.
Over to you, Milan sir.
Yeah, thank you, ma'am. Thank you very much, Ali sir, for your valuable comments.
Hey,
thanks to all participants for participating in this discussion. So now I like to request Mr. Pratik to introduce our next speaker. Over to you, Mr. Pratik.
Thank you, Milan. Proceeding towards another eminent speaker of the day, I would like to introduce to you to Professor Gaurav Srivastava. Professor Gaurav is presently working as a faculty member in the discipline of civil engineering and is also the coordinator of the Center for Safety Engineering at IIT Gandhinagar. He did his PhD from the Department of Civil Engineering, University of Minnesota, USA, and was a postdoctoral research fellow at University of Notre Dame, USA. His professional and research interests involve assessment and design of structural and non-structural building components subjected to fire. He has worked towards analysis and design of reinforced concrete and steel structural systems subjected to fire and assessment of building facade systems and their components under fire. He has published more than 70 papers in refereed journals of high repute, international conferences, and book chapters. He has co-edited book published by Springer Nature. Professor Gaurav has excellent research contributions in terms of research publications in journals of high repute, research supervision at PG and PhD level, and handling number of research and industry consultancy projects, including projects supported by Underwriter Laboratories, Uchchatar Aviskar Yojana, TBRL DRDO, Hilti, and many more. Professor Gaurav has proven administrative skills by accepting different challenging administrative assignments. Presently, he is serving as a Dean of Campus Development at IIT Gandhinagar. He has also received Excellent Faculty Award in Institutes Building from IIT Gandhinagar. Professor Gaurav is going to talk on multi-physics nonlinear analysis of building structural systems subjected to fire. Now I request Professor Gaurav to take over the session. Over to you, sir.
Thanks a lot, Pratik, for the kind introduction. And good morning, everyone. And thanks for giving me this opportunity to talk in this conference. So, my topic is dealing with effects of fire on structural systems. And I'm sure all of us come across through different news items every now and then that different sort of buildings throughout our country keep getting into fire. One of the most recent ones I think was just a couple of days ago in Surat. There were 3 blasts followed by a fire in an ONGC plant. The agenda for today's talk is going to be, how does this fire affect the structures? So all of us obviously know that fire is a hazard to life, but I will perhaps talk a little bit more about how can it affect the building. So this is the outline of the talk. First, I will briefly talk about the what is the hazard due to fire for buildings. Then I will go on to the elements of physical modeling, followed by the mathematical modeling to be done in case we want to simulate the effects of fire on structural systems. Then I will discuss the numerical solution scheme that we had used to solve these questions, followed by some verification and validation studies to show that this framework developed by us, how closely it can mimic the real life scenarios. Finally, I will present a couple of case studies on actual analysis of buildings subjected to fire. And finally, I'll try to conclude with some takeaway points. So just a brief overview of fire hazard on buildings. So if you see this first graph, this shows the fire deaths. So this is 2010 data. But what comes out quite clearly is that India was number 1, at least at that point of time. So with almost 25,000 deaths happening due to fire in India, with respect to the next country was China. Whereas if you really see, China's population is much more than in India. And some of the countries like US were at 3,000, like UK were at 500. So basically, this outlines that the issue of fire safety in India is quite blatant, and it's very, very important. In terms of how the fires were classified, this pie chart shows a little bit there. So, of all the fires that happened, around 37% were structural fires. And when we say a fire was a structural fire, it means that the fire has sustained long enough to become a threat to the structural system. And hence, it is a threat that the building itself may fall to fire. And one of the most notable examples of course, fire leading to the collapse of a building was the World Trade Center accident, or rather the terrorist attack which happened in 2001. Now, many people believe that the buildings fell due to the impact of the aircrafts, but that was not the case. The buildings were in fact designed to sustain an aircraft impact. The buildings actually fell because of the fires that happened after the impact. So a lot of jet fuel was spread throughout the building, which caught fire, and that burned at extremely high temperatures. So the buildings fell due to the fire, not really due to the impact. Okay. And another more recent study revealed that every 5th fire death in the world is in India. So what it means is that if throughout the world, if 100 people die, every 5th of them, which means almost 20%, are in India, which is a huge number considering that land area wise we are not that large. So what it obviously means is that fire safety has to become an important agenda for us to be able to sustain the growth. So nowadays there is a lot of emphasis on taller buildings, newer buildings, more habitable zones. The cities are expanding, etc. So overall, fire safety has to become more important for us. So if I were to explain the overall fire safety strategy of a building, that can be done through these. There are 2 graphs here. So these graphs are between the temperature and the time. So on the x-axis here is time, and on the y-axis is temperature. Now this blue curve shows the behavior of an actual fire. Okay. So what happens in an actual fire is that first there is some initial ignition. So imagine that at the corner of a room there is a small piece of furniture, or there is a small electronic appliance that catches fire. So for some time that fire will remain small. So that is called the ignition and smoldering stage, where the fire is small, and it can range from 5 minutes to 20 minutes depending on the kind of ignition and the kind of furniture that is in there. And all the life safety aspects, for example, if fire alarms have to function and automatic sprinklers have to function, that has to be done within this 20-minute window or 5-minute window. So if someone has to use a manual extinguisher or call the fire station from inside the building, that has to happen before this. If people have to evacuate out of the building, that has to happen before this time. And what happens after the growth phase starts is that around this time, when the initial ignition and smoldering transitions to a growth, this growth becomes very rapid, and this period of growth is called a flashover. Okay, and the flashover is a time when a small compartment fire or a small room fire suddenly engulfs the entire. And I mean, this is a very dramatic effect where an initial fire at one corner of the room suddenly engulfs the entire room. And once that happens, that stage is called flashover, and beyond that is called the post flashover range. And in the post flashover range, the temperatures are well beyond 700-800 degrees Celsius, and anyone or anything remaining still inside the building in the post flashover range, the chances of survival are extremely low. Okay. And it is during this time where the structural fire safety becomes important. So what it means is that once the temperatures go beyond 700-800 degrees Celsius and the fire has been burning for some time, maybe 30 minutes or 1 hour, that is where the structural fire safety becomes important. What it means is that the firefighting operations will continue well beyond the growth time. So chances are that in India, if you make a call to firefighting station, they will take about 20-30 minutes to reach. And by that time, the fire would have already passed the flashover stage. Okay. And once it reaches the flashover, then the firefighters will have to go inside the building during that fire. So the safety of firefighters depends heavily on structural fire safety. And of course, the recovery of the building. So once, let's say, the fire has been doused and the building is to be reused again, then again, the fire safety of structures, the structural system becomes important. Because if the building undergoes major failures in the system, for example, if a slab falls or if a wall falls, then the retrofitting or rehabilitation of the building becomes that much more challenging as well as more costly. So if we have better structural safety provisions to start with, the post-fire recovery can become faster and more economical. Okay. Now, what are the effects of fire on real structures? So these couple of photographs show the effects on steel structures. You might have come across at least 2-3 types of structural systems. One are the steel structures. So if you have crossed any old railway bridge, you would have seen large steel I-type beams which are connected through large bolts or rivets. Right. So many industrial buildings are made using those steel structures. And when these steel structures are subjected to fire, they undergo very large deformation. So you can see this. This would have been a very perfectly straight column, but due to the effects of fire, this has bent to a very large deformation. It undergoes permanent plastic deformation. So imagine if you have a steel ruler, which is one of the common things which many students have. So if you bend it and release it, it will regain its original shape. So that is that deformation was not permanent. It was a temporary deformation. So if you release it, it goes back to the original shape. Whereas during fire, if it undergoes large deformations, it bends like that and then remains in that position. Okay. So that is a permanent plastic deformation. So it cannot come back to its original position. The material properties are temperature dependent. So if you have to apply a certain force to bend a beam in room temperature, at a higher temperature, that requirement of that force is much smaller. Okay. And then it can lead to instability. Instability means it can just overturn. So here you see that the entire thing has just fallen down. Okay. So instead of these columns being able to support the system, they have become unstable and they are just falling. The other kind of structural system you might have seen is a reinforced concrete or RC type structure. These are more common in India, especially for residential and non-commercial buildings. These typically have a reinforced concrete frame, and in between there are masonry fills, which have brick and mortar. Right? So reinforced concrete structures, although are believed to be better in terms of fire performance, because concrete is a natural insulator. But still, if it is exposed to fire for prolonged periods of time, there can be severely adverse effects. So they can also undergo large deformation. So this beam, if you see, has deflected quite a bit. Okay, they can have permanent damage. So now, unlike steel, in concrete, chunks of concrete can come out, okay, and these cracks can form. So these cracks, once they are formed, they cannot heal. So that is sort of a permanent damage. So this crack will remain even once the fire is done. Okay, and these chunks coming out is called spalling. So this happens because in concrete there is some water inside, and once heated, that becomes vapor, which exerts some pressure and it causes the concrete to explode. Of course, the properties are still temperature dependent, and in concrete structures also we can have effects of instability where the entire structural systems can collapse. You may recall that last year there was a fire in a silk sari mill in Chennai where fire burned for a while, but after that the entire roof of the building collapsed. That happened because of. Based on these, what are the elements that we should consider in physical modeling if we are to predict the behavior of these structural systems? So one of them is large deformations. So for both steel and concrete structures, we see that the deformations can be really large. Second is heat transfer. So from the fire to the structure, there will be some heat transfer. And then within the structure, within a column or within a beam, there will be heat transfer. There will be moisture transport. Now this moisture transport is more relevant to concrete structures because concrete essentially has some amount of water which it has. After curing period is over, it will have 3 to 10% kind of moisture content. And when there is a fire or a high temperature exposure, this water will become vapor and it will diffuse inside the concrete, and that can cause problems. And then there are issues at connection. So wherever these beams and columns are joined together, they need some special type of treatment, especially with respect to steel structures. So moving on to mathematical modeling, heat transfer is typically modeled by the simple diffusion equation, heat diffusion equation. Okay. So this imagine is a cross section of one of the columns or the beams here. So inside we will consider heat conduction, where rho and c are the density and specific heat, and k is the conductivity of the material. And in all of the real structures, all of these three parameters, all of these two parameters, specific heat and conductivity, are temperature dependent. So which means with temperature they will change, and that essentially makes this equation a nonlinear equation. It doesn't remain a linear equation. Now from the fire to the surface, there is heat transfer through convection and radiation. Okay, so this is being applied as a boundary condition, and it is possible that a column or a beam will have one side which is exposed to fire, but other side which is not exposed to fire. So from that side, it may try to cool itself. Okay, so this is the natural convection or radiation. So if on the other side there is a temperature, there is a room temperature which is not exposed to fire, from that side this particular body will lose heat through convection or radiation. So this is the overall picture for heat transfer. For moisture transport, we have a similar equation. Moisture diffusion is also modeled through the similar looking equation. Just that we have here converted the moisture transport problem to a pore pressure diffusion equation. And this is being done through the Bazant's isotherm and using the ideal gas law. So when we use the ideal gas law, the mole fraction can be converted to partial pressure. And that is what is being done. So basically we are modeling the pressure diffusion inside a column or a beam. So again, this particular boundary shows inside of the gray area shows the inside of the structural member, where we would consider diffusion of pore pressure with this equation. And again, this Kp and A will be temperature dependent properties of the system. And throughout all of the four boundaries, okay, there will be a convective mass transfer from the surroundings. So the surrounding air also has some humidity. So we have heard that around monsoon time the humidity is close to 100%. At other times it is 60%, 70%. So whatever that number is, that will also contribute to the moisture transport for the member. So at the boundaries, we have considered convective mass transfer to the structure. And this image on the right just shows the phase diagram of a typical concrete structure. So there are aggregates. So if you have, I'm sure many of you would have seen how concrete is made. So there are stones, big stones, which are in technical terms they are called aggregates. There is sand. Sand is also called aggregate. So aggregate here is representing those stones and sand. Then there is a amount of cement which is added. There is some amount of water which is added, and at room temperature there will be some air. Okay, so at room temperature concrete will comprise of aggregates, cement, water and air. But at higher temperature some of this water will convert to water vapor. So that is what is causing this pressure, and that is pressure we are modeling through this pressure deformation. Deformations are modeled through the usual elastostatic equation, where we say divergence of the stress plus the body force B is equal to 0. So this is an elliptic equation. So the earlier two diffusion equations were parabolic PDEs, both non-linear, and this one here for deformations is an elliptic PDE. So divergence of stress plus B equals to 0. And one interesting thing is that the total strain we have to decompose into a few components. So E denotes the elastic component of the strain which causes this stress. This TH denotes the thermal strain. So this is due to the thermal expansion of the material. And you may all relate perhaps it with the alpha delta T type of thing, where alpha was the coefficient of thermal expansion and delta T is the rise in temperature. C denotes the so-called creep strain. So creep strain is something where even if you have a constant load, a material may undergo deformation, and that deformation is termed under creep. And then the last component is TR, which is the transient component. And this transient component is basically whatever is not covered by the first three components is covered by the last. So that is more like an experimental factor. Now, how do we combine the earlier, three different physical phenomena? So heat transfer, mass transfer, and mechanical deformations. So one obvious way might be we can consider a full three-dimensional finite element model, where these three equations can be solved in a coupled fashion. Okay, and there are indeed software packages which do that. But because of the nature and complexity and nonlinearity and interdependence between these three different equations, a full finite element procedure becomes extremely costly. Computationally, it becomes very, very expensive and sometimes intractable. So while it may work for smaller systems, for example, one beam or two columns or one slab, but for a large structural system, it becomes extremely difficult to actually formulate that using a full element. So we have adopted in this case what we call a two-level discretization strategy. Okay, so imagine that this thing shows a beam. Okay, so along the beam, what we have done is that at the cross section, along the length we consider different cross sections. So here we have, let's say, I-1 is one cross section. At I we have considered another cross section, and this I+1 is another cross section. And this along the length we consider different cross sections. So along the length we have a 1D mesh in a way. So this entire cross section we idealize with a single line. Okay, so one beam becomes a sort of a 1D line element. where it is shown like this. So along the x, we have I minus 1, I plus 1, and so on and so forth. We can have different nodes. This will serve as a 1D mesh for the structural analysis, for the mechanical analysis. Okay. But we know that the heat transfer and moisture transport are phenomena which will happen across the cross section also. So throughout here also you will have heat and mass transfer. Okay. So in the YZ plane. So in the YZ plane, which is the cross section, we consider 2D mesh, and on this 2D mesh, the heat and mass transfer equations are solved using a finite element scheme. Okay. So basically, we have a 2D finite element mesh where we are solving heat and mass transfer, and we have a 1D finite element mesh where we are solving the structural analysis problem or the mechanical deformations problem for a beam. And how they are linked is being shown in this figure. So if we have two cross sections, let's say one from I and one from I minus 1. So each cell of the finite element mesh is linked to the corresponding cell of the next mesh through a set of lines. And these set of lines are combined and in an equivalent manner and converted to a single line where the So this is what is being done for a beam, but for a slab, the situation is slightly different. For a slab, the 1D mechanical deformation cannot be considered. So we consider a two-dimensional sheet. Okay. So here, in general, what would happen is that let's say fire is below the slab, so the bottom layer will be subjected to fire, but the top layer will be subjected to ambient temperature. So taking advantage of that in the y direction, which is the depth direction for the slab. So now here the heat and mass transfer can be converted to a one-dimensional problem, where along the y direction we do heat and mass transfer. But the mechanical deformations have to be a two-dimensional problem, where we consider the xz plane entirely for a two-dimensional. So now here we have the mechanical problem being solved as a two-dimensional problem in the YZ plane, and the heat and mass transfer problem being solved one directional, the y direction, as a 1D problem. And again, these two are linked in a way similar to what was done for this. Okay. Now, moving further on the numerical solution scheme, so the heat transfer problem of 2D FEM, this we are solving using the generalized trapezoidal method. So basically, once we discretize the convection diffusion equation using finite element, we will get this form, which is a semi-discrete form. M and K are the semi-discrete matrices which are coming from the finite element discretization, and T here denotes the nodal temperature. But at this stage, this is still continuous in time. Now, to discretize this in time also, we use the generalized trapezoidal method. So after that, we get this equation. So this is an equation which can be solved iteratively for Tn plus 1, the temperature field of the current step. And beta is a parameter. So if beta is equal to 0, this scheme will become an explicit Euler scheme, which is first order accurate. Beta equal to 1, then this becomes an implicit Euler scheme, which is first order accurate. Obviously, the difference is that in explicit Euler, there will be some restriction on the delta t, or the time step, or tau, which is here. Whereas in case of implicit Euler, this scheme will be unconditionally stable in time. And there is another interesting value of beta which is useful. So beta equal to half gives the Crank-Nicholson scheme, which is also which is not only unconditionally stable, but it is also second order accurate in time. So for greater accuracy, we can use beta equal to half. A similar scheme is used for mass transfer, where we are modeling pressure diffusion. So this is the semi-discrete pressure diffusion equation, and once we apply the generalized trapezoidal rule, this is what we get. Again, this is similar in terms of the terms, similar to the heat diffusion equation. Now, one interesting or important thing specifically for concrete structures is that we need to use a spalling criteria. So if you recall that photograph where there were chunks of concrete which were taken out, or which fell off from the beam. Now, once that happens, the cross section changes, right? Once the cross section changes, then the finite element mesh on which the heat and mass transfer problems are being solved, that would change. Okay, so to incorporate that at every time step, there is a check that if the pore pressure is greater than the tensile strength of the concrete, then that portion of the concrete will be assumed to be fallen off. That is the spoiling criteria. And once that happens, then both of these solution schemes will have to update their meshes, because now the boundaries have changed. And that is graphically shown here. So if the pore pressure buildup at a particular point is shown by this red line, and the tensile strength of the concrete is shown by this black line. So at a time or temperature wherever this red line catches up with the black line, that is where that portion of the concrete is assumed to be spalled off, and the geometries have to be updated. Okay. And in this case, you can also see one more thing, that the tensile strength of the concrete is going down with temperature. So this is what I mentioned, that with temperature, the properties will change. So in general, the strength of concrete and steel both reduce with rise in temperature. Now, recall that I showed that the mechanical deformations were converted to one-dimensional finite element systems. And that is being solved using something called a matrix method approach, which is a specialization of the finite element method. So we do consider, a particular beam or column element with certain degrees of freedom. And eventually, these are the governing equations which can be derived for these systems. So we are modeling the centroidal axis of each beam, where there are two meshes, one at the start, one at the end. These are the meshes where the heat and mass transfer problems are being solved. And you may recall that we have connected each of these cells corresponding to one another, and all of them combined will lead to one centroidal axis where the mechanical deformation problems are being solved, and that is being shown here. So here Z denotes the deflection in the Z direction, and Y denotes the deflection in the Y direction. So there are two bending deflections that we are considering. Now for the shell element, it has to be a full shell element which was developed. That is a two-dimensional shell element. Okay. The connections between two columns or two beams, or a beam and a column, these are being modeled using zero-dimensional spring elements. So this is like a torsional spring or a translational spring at the joint. And finally, the permanent plastic deformations, especially for steel, they are being modeled using a distributed plasticity approach, where this stress versus strain is the idealized stress strain graph of steel, which is shown. So this is how a steel will behave at different temperatures, and this is parameterized by temperature. So this capital T in the subscript shows a parameterization with respect to temperature. And this slide just shows the material behavior. So basically, for concrete at different temperatures, the strengths are different. So this is in compression and this is in tension. So this is another complexity that arises, that for concrete, the behavior in compression and tension are different. So this is the overall integrated approach, where for a typical frame, this is the slab, these are the columns, these are the beams. So the slab, we have a multi-layered approach. At the junction, we have a zero-dimensional element, and for column or a beam, we have this one-dimensional mechanical element. This is the overall approach, and the algorithm goes like this: that we know quantities at a certain time from the initial conditions, and then we start with a certain time step, and we compute the fire temperature. That fire temperature is applied, and all of these three solvers are iteratively solved until there is convergence. If it is converged, then we accept that time step. Otherwise, go and reduce the time step, change the time step. Okay, so I'll now move on to some verification and validation studies which were done to check whether this framework which we have developed is accurate or not. So this one shows a beam like this, which is fixed at this end, and there is a temperature gradient being applied, a linear temperature gradient on the cross section being applied. So for this, there is an analytical solution which is possible. This delta H and delta V are the horizontal and the vertical deflection of the at the end. And the graph here shows the theoretical versus the computed values. And these are in most exact agreement. So this gave us some confidence that this framework is doing well. Now, another important aspect that this framework had to capture was permanent plastic deformation. So for this, we considered an experimental data set where a beam of this kind, which is supported like this on two ends, it was subjected to a temperature gradient or temperature profile of shown here. And there was a heating and a cooling cycle. So here also, if you see heating, the deflection goes like that, and cooling, there is some recovery in deflection, but eventually there is some permanent plastic deformation of almost 50 millimeters. Okay, so this also we were able to capture quite nicely. Then we moved on to a slightly bigger problem where this is a space frame where there are multiple beams and columns, but as of now there is no slab or no walls. So here also, our computations were in good agreement with other simulations which people have done earlier, and the other simulations are actually using the full finite element method. So that also shows that this simplified finite element type of approach is able to capture what a full finite element approach is able to capture. This shows so earlier 2-3 examples were for steel. Now this example is for reinforced concrete. So this is where permanent damage, etc., becomes important. And here again, we have compared the temperature as well as the displacement at certain points. So the temperatures match well with experimental, as well as the deformations also, match well with experimental. And also we have tried to compare our results with Saphir, which is a software which uses a full finite element type approach for fire analysis. This is a column which is fixed on both sides, again reinforced concrete, and again we have tried to validate our framework. So here this graph on the right shows validation of temperature data, and the graph on the left shows validation of the displacement or the deformation data, and both of them agree reasonably well with experimental results. Next, we moved on to a slightly more challenging example. This HSC represents high strength concrete. High strength concrete nowadays being used more and more, and the problem of spalling, where chunks of concrete fall off during fire, that is more prevalent in high strength concrete or high strength concrete members. So here we are plotting percent of spalled concrete with time. And again, we are trying to compare our results with experimental data, and it matched quite well. So what that meant was that our pore pressure solver and the spalling criteria with respect to the tensile strength of the concrete was working well. And these cross sections here are showing the spalling profile. So initially, this entire beam is intact. After 1 hour, these black the black things on the side are the concrete things which have fallen off. Okay, so this is how it has. Then we did validation of a slab. So earlier validations were with respect to beams or columns. Now for a slab also, our the central deflection for a simple fire exposure, experimental versus computed, was in good agreement. And of course, from a computational model, we are also able to extract what will be the cracking patterns later on in the slab. So X figure shows that cracking pattern derived from the computer model. So then I'll just present a couple of case studies. So this is a 20-story steel building which was designed, and in this we have considered a traveling fire scenario where fire starts somewhere here and then it keeps on moving up. Okay, and this is a scenario which is oftentimes seen. Fire starts at a lower story, then it begins to rise up. And what we're able to predict from our framework is how the deformations will look like, how the temperatures will look like, and for looking at a particular structural member, we are also able to predict what is the time to failure. So, for example, for this building, somewhere around 24 minutes, this entire building might fail. That is what the prediction is in this case. One more example of a reinforced concrete building where there are multiple columns and a slab. So this is one example with a slab. Okay, and in this case also we are able to predict what are the deformed shapes, how the slabs will deform. We can calculate or we can get deflections of particular points on the beams or columns. So this can also help us in seeing which areas are to be protected more, which areas are to be protected less, under what kind of fires. Now to sum up, what I've basically presented is a multi-physics modeling approach for structures under fire, considering the three main physical phenomena that happen. So heat transfer, mass transfer, and mechanical deformations. And all of these are linked to each other. So for example, heat transfer will give a temperature rise. That temperature rise will go into a thermal strain, alpha delta T type of thing, right? Now from mechanical deformation, we will know when the spalling has occurred. That will update the geometry for heat and mass transfer. So these are interlinked phenomena. And these are highly nonlinear because the material properties are temperature dependent. And full finite element treatment can be computationally very, very, very intensive. That is where this hybrid two-stage approach was shown. Showed validation and verification of this framework with several cases. Of course, there are many more which we have done, but in this I have not shown all of them. And then finally, what we've seen is that how useful this kind of can be in assessment of real buildings. So I would like to acknowledge Dr. P. Ravi Prakash, who did all of this work during his PhD. Currently, he is an assistant professor at IIT Warangal. And also, I would like to acknowledge the support from Center for Safety Engineering at IIT Gandhinagar. And yeah, with that, I'd like to stop. Thank you very much for your time. If there are any questions, I'll be happy to take.
Thank you very much, sir, for your valuable and interesting talk on building structural systems. Taking advantage of being part of this platform, I would like to ask you one question, sir. We have seen that fire safety parameter has become one of the very important parameter in the era of high-rise buildings. We have also seen many schools and coaching classes are running on 7th and 8th floor of the building. And many horrible incidents have taken place in recent past. So I would like to ask you that what are the minimum fire safety parameters that need to be considered in the structure of a building for school purpose or academic purpose?
So these things are actually nicely laid out in our building codes. So there is a National Building Code of India. And it is expected that all of these buildings will conform to the requirements which are mentioned there. And in my view, if these buildings really follow those norms, then these kind of incidents will drastically reduce. So the Surat incident which you are referring to, that happened. That was actually a blatant denial of these norms which are there. So the seatings which were used were made of tires which are highly inflammable. The exit routes were blocked, and there were many issues in that. So there are many. These norms are very nicely laid out in the National Building Code. If they are followed, these kind of incidents will not be there.
Okay, thank you very much, sir. Ma'am, is there any question from your side?
Yes, I have one question, Gaurav, sir. Day before yesterday, there was a blast in ONGC, Bharuch.
Yeah.
So can it be reduced? Because all the companies are using norms set up by fire safety. But then why it is getting done again and again, particularly in ONGC?
So there are two aspects to it. One is the so-called fire safety norms, and for these oil companies, there are another set of norms which fall into the process safety region. So, process safety means that they are doing processing of these petroleum products here and there, and they need to follow certain practices and checks and balances. A few years ago, there was another similar thing at IOCL. And by default, these industries are very, very high risk industries. So more than structural safety aspects, I think process safety aspects apply more to these industries. And what we have seen in most cases that these accidents happen primarily due to human error. Sometime back in Hyderabad, there was a gas leak. That was also a consequence of this process safety hazard. And I mean, I would even say that some part of it is perhaps due to lockdown because things were suddenly stopped. People might not have had a chance to look at whether a particular valve is off or on. There would be a certain capacity for holding things. So routine inspection, training, and awareness for the operators, I think that is what might reduce these things.
Okay, sir. Thank you.
Thank you.
Thank you very much, sir. Due to internet connectivity, I lost in between, but I will.
So lost again.
Yeah, thank you very much, sir, for your answer. And also thanks to all participants for participating in this discussion. So moving on to the next session, our next speaker is Dr. Prashant Kumar. Dr. Prashant has been working on applications of the satellite data in numerical weather prediction models in Space Application Center, ISRO, since 2008. He completed his PhD in Applied Mathematics from Motilal Nehru National Institute of Technology, Allahabad, India. He customized and implemented the weather research and forecasting model and variational data assimilation method for operational weather forecast from Space Application Center ISRO. He published 64 publications in international peer-reviewed journals with a total impact factor of 182 and various ISRO scientific reports. He developed a procedure for assimilation of nonlinear and non-Gaussian satellite observations in the numerical model using the particular filter method. He is fellow of Indian National Young Academy of Science, Indian National Science Academy, New Delhi, and Association of Indian Academy of Science, Bangalore, India. He received Ministry of External Affairs Young Research Award for year 2018, Indian Meteorological Society J. Das Gupta Award for the year 2016. He received the ISRO Team Excellent Award twice in 2011 and 2013. So now I would like to invite Dr. Prashant Kumar for his talk on data assimilation in the numerical weather prediction modeling. So over to you, Dr. Prashant, sir.
Thank you very much, Patel. First of all, I am thankful to Professor Shah, Dr. Akansha, and all the organization committee for giving me this opportunity to present my work in the Space Application Center to the community. So okay, so now my presentation is on the data assimilation in the NWP modeling. So this is the most focused area in the field of the weather forecasting and atmospheric modeling as well as in ocean modeling, where people are using the numerical models or dynamical models to predict the weather or ocean states. So within this, when we use the huge number of satellite observation as well as ground observations, how to club these observations in the numerical model, that technique is known as a data assimilation. And the biggest computer in the world, like petaflop type of machines which are used worldwide, those type of machines are used here for the applications of the data assimilation. If I will give you just one example, so if a particular weather forecast model required a around 20% time of the full big HPC petaflop machine, 60% time is taken by the data assimilation technique. So that much huge computational resources are required for the data assimilation. So with this, I start my presentation. So this is just one example that shows that data assimilation can be used for the various mathematics field, like its base is depend upon the probabilistic forecast, string, Bayesian data assimilation, as well as functional analysis, numerical analysis. So various type of pure mathematics as well as applied mathematics is the base of this field, and huge number of mathematicians as well as physicists are required to develop these techniques. So with this, we have a different kind of problems. One problem which is purely based on the mathematics or physics of the problem, as well as there is another problem which is based on the forecasting, decision support, like within the Indian Meteorological Department, Ministry of Earth Sciences, Ministry of Forests, those organizations are taking care of the forecasting, decision support, how community will be welfare by these purely physics based events. So with this, I start with what is a model. So there are a various kind of models which are based for predicting the atmosphere. So there may be a kind of model which is based on the thumb rule, like heuristic model, or empirical model, which is based on the prediction of the past behavior. With this, because these models which are used in the weather forecasting, they are opt from the basic law of physics, like conservation of mass, momentum, energy, ideal gas law. So whereas in within this equations, there are few problems which are a very complicated non-linear partial differential equations, and the solution of the analytical solution of those equations are still not possible. So because of those reasons, people are think about that numerical solution is only the possible way to solve these big equations. And the another difficulty with this problem is that we have a huge number of grid points in the numerical analysis, because here we are considering the global models where we have a all the latitudes and longitudes. With this, uh, we are going to the towards the higher and higher resolution. Previously we run the numerical model at 25 kilometer or 100 kilometer. Now people are thinking about 1 kilometer, 2 kilometer resolution. So if you roughly consider, the problem is of the order of 10 to power 9 or 10 to power 11 degree of freedom. So this much huge complexity is here due to the numerical approximations. And with this, because we have a very big uh, computational matrix here, so we required a huge computational resources, and that's the reason the most biggest system available in the world are used for the weather applications. So with this, if we have a dynamical model which can be represented as a xk plus 1 is equal to model m xk plus a error term wk plus 1, where my model is in Rn, and for simplicity we consider that the time are discrete here. So here the model M may be a linear model as well as a non-linear model, but in most of the applications we have a non-linear models here. And again, the error which we consider here as a wk is known as a model error, and this model error is also not have a very perfect distributions. Now, when we consider that we have observations from satellite or from the conventional observations like radio sondi, which launch from the weather stations, or some ground observations like the automatic weather stations, buoy from the ocean. So those observations also have a different kind of nonlinearity. Means the weather parameter which are available from the models are, and the observations which are available from the observation network are not maybe the same metrics. They have a different form. Like if I give one example, like if we want to give a prediction for the basic parameter winds, UV, temperature, moisture, etc. Whereas satellites gives us the brightness temperature. So how the different weather parameters are linked with the satellite parameter, which is available as a brightness temperature. So those also required a kind of a functions. which we call here as a observation space. But again here we consider that observation Z is based on some function of H, which is a transformation from the weather parameter to the observation space. Like observation space is here the brightness temperature which is available from the satellite, and again here is a some error Vk which depend upon the model H. So again the model H may be linear here as well as non-linear. So with this, I want to give one example that why we need to combine the different set of observations. Suppose we get one observations from the satellite and another observations from the model. So why we need to combine this? So based on the linear estimation theory, we found out that if we will optimally combine the two different information available from the two different sources, the two different sources are here, one from the satellite or ground observations and other is the previous estimate of the weather, which we normally call as a background or analysis. So when we combine these two information, background and observations, and optimally combine these two things, what we found that is called as a analysis of a present state of the atmosphere. And based on the previous mathematics, we found that an error in the analysis is less than the error in the observation itself as well as error in the background. So that's the reason we need a very good setup of the data assimilation technique. So with this, now I start a data assimilation. What is the data assimilation? So data assimilation is a technique which combines observations with the first guess, which is generally called as a output from a numerical model. So suppose I gave a prediction for next 6 hours. So that prediction is considered as a first guess or background or prior estimation. And the observation which are available at that time is considered as a likelihood. So based on the Bayes theorem, what Bayes theorem told that if we have a prior estimations and likelihood of the distribution, we can get the posterior estimation, and that is the base mathematical foundation of the data assimilation, which depend upon the Bayes estimations. So if we have a prior estimation and likelihood means observations from other sources, by combining these two, we can get the posterior estimations. So why we need data assimilation? So the first and foremost requirement is that we want to create a initial and boundary state problem, because these equations are numerical weather prediction model are mostly the partial differential equations, and the accuracy of the initial and boundary state is very important in these equations. So the most important part of the data assimilation is that they are used to improve to the initial state of the atmosphere. With this, we also use these data assimilation technique for the various sensors, which means what kind of instrument or observations are required for future applications. So those type of sensor requirement are also required given by the data assimilation technique. With this, we are also preparing a various kind of reanalysis. Reanalysis means, suppose if someone want to study the long-term behavior of the atmosphere, like from 1940 or 50 to till date, so various kind of reanalysis are available globally. So those reanalysis are also required in detailed techniques of the data assimilation. Like from India, we have a NCMRWF reanalysis, National Center of Medium Range Weather Forecast. This center is situated in the New Delhi. With this, there are a huge number of applications based on extreme weather event, tourism, air pollution, etc. So with this, data assimilation is also used in various other fields, like in the share market, economics, as well as in the ocean modeling, ocean forecasting. So there are various places where data assimilation technique are used. So the aim of data assimilation is that we have a very few observations in comparison to the large number of model grids. So if I give you just a brief that the model grids are, if we will consider 0 to 360-degree longitude, and 1 degree longitude is roughly 100 kilometer, 10 kilometer over the equatorial region. So around 360 into 100. If I want to run a model at 1 kilometer over globe, we have a 360 into 110 grid points in the x direction only. Then similarly, in the latitude direction, means in the y direction, also we have a huge number of grid points. Then again, we are considering the vertical levels, means from surface to the altitude of a 60 kilometer something. Then we have a different model parameters. So if we will multiply all the parameters together, we will get the degree of freedom of the model is approximately 10 to the power 9 to 10 to the power 11. Whereas in comparison to this number of degree of freedom, we have a very less number of observations which are available from all set of satellites as well as all ground observations. So definitely there are various kinds of error. The error which is coming in the first guess means the first guess is which generally called as a few hours forecast from the earlier model run. Like for today, if we will take the yesterday forecast, which is valid at today, that is considered as a first guess. So this first guess is also have a error. This first guess is also known as a background or priori estimation. With this, the model which we are using in the weather prediction or ocean predictions, they are the numerical approximation of the very complex physics. So definitely when we are using the finite difference method or finite element method, now people are using make use of finite element method also. So those scheme also have some kind of error. To implement these scheme, with this there are various kind of approximations of physics also, like which normally we call as a parameterizations of the cloud, because we cannot run the model at the very small scale of the cloud scale, like 200-meter or 50-meter. So we approximate various physics, so that also contribute a error in the numerical models. With this, whatever we get from the satellite or from the conventional observation like radio sondi, because radio sondi, when we launch the radio sondi is also drifted, because means if I give just one example, if we launch a balloon from Ahmedabad, it will drift up to 30 to 40 kilometers from the Ahmedabad location. So it is not giving the precise estimations of that location. It is drifted with the as its altitude is increased. So with this, we have a very just limitations of data assimilation technique, because errors can be random or a systematic error. So if errors are systematic, we can use some mathematical techniques to correct the errors in the prediction. But if errors are random, so it's a very complicated problem at that time. And with this, there is a intrinsic prediction limitations, which is based on the very famous theory of the Lorentz chaos theory. Means if we will use a very precise, accurate estimation of the initial state after a certain time period, the numerical approximations are not very precise. Means in the conditions of the weather model, after 15 days, if we will use almost similar initial state, the prediction may be very wrong. So these are the inherent limitations of the weather prediction model. So if I give you just one example of data assimilation, so we have a true state which no one knows, it's an unknown states, but in between I have few observations which marked as a yellow here. So when we start our model from the analysis ANA and give the model simulations and reach the forecast state, what we get, our forecasts are very far from the true state trajectory or from the observations. So then we use the if we will run further with this forecast state, my model will be very far from the true states. So what we did here, we use the data assimilation technique at this time step and try to find out the analysis, which is the best estimation of the observation as well as forecast. So this is now my analysis. So this is the place where we use the observation and forecast and make use of the various mathematical technique and try to find out the analysis which is more precise as compared to the forecast, earlier forecast. Then we again make a prediction from the NWP model. Again, my forecast is far from the analysis. And then again, we did the data assimilation at this step and try to find out the analysis. So this is the systematic behavior of any operational weather center where people assimilate the observation and make use of the various satellite and ground observations, prepare the analysis, and then give the forecast for next 5 days or 15 days. So this is a typical regional or global data assimilation system example where we have two different of observations, set of observation. One is observations from the satellite as well as from the grounds. Another is a background, which is a forecast from my earlier runs. Then we use the data assimilation, prepare my initial condition, run the NWP model, and give the operational forecast for 3 days to 5 days or 10 to 15 days. And then the short forecast from the NWP model, 6 or 12-hour forecast, is again considered as a background for the next cycle. So this is the cycle which is running in almost all the centers worldwide. In India also, we have a operational center of Indian Meteorological Department. So there also people are running this cycling and make use of the weather prediction. So there are the fundamental issues in the atmospheric data assimilation. The first and foremost important thing is that this problem is a underdetermined problem. Means we have a very less observations as compared to the model states. Another issue is that the forecast as well as observation both have an error, and we require the covariances of these errors. So, and finding the covariance, precise covariance of these observations are very difficult. And another most important example is that we have a very nonlinear chaotic dynamical system with very large scale problem. So there are various techniques based on the computational resources, start from the objective analysis, optimum interpolation, variational method, Kalman filter, and particle filter. And right now people are working on the various kind of different nonlinear filters. So again, when we goes from the objective analysis and OIE to the variational method of Kalman filter, the cost of computational is increased manifold. If I give just one example, for a particular application, if I use 3D VAR method, three-dimensional variational method, it will take hardly 5 to 10 minutes. Whereas for the same applications, if I use the 4-dimensional variational method, it will take around 5 to 6 hours. So that much computational requirements are there when we increase a particular technique from the. So this is just one example that what is the objective analysis method. It is a very simple method used in the 1949, 1959, developed by the Pressman. What he told that if within a model grid, if we have a observations which is represented here as a yellow star, so what we can do based on the radius of influence, we can find out that this observation have a maximum impact on these grid points. And based on some distance formula, we can find out that this particular observation have a maximum impact here. But the issue is that within the true trajectory, whenever observation came, what happened? This particular data assimilation technique give more weight to the observations, and my trajectory, my balance of the fields are disturbed, and because of that, the stability of the models is loose. So that is the reason people did not believe on this technique. But this is the start when numerical models are started by the around 1922 by Richardson, and then in 1949 or 1935 by Professor Charlie. So at that time, people think that this kind of techniques may be possible where we can make use of the observation. At that time, mostly observations are coming from the very grounds type of sensors. So at that time, people think that it's a very uh, unique thing that people think at that time that this type of technique may exist in future, and weather can be predicted. If I give you just one example, that when Richardson did his unique experiment of the weather factory, he found a very large error, around 150 Pascal error, hectopascal error in the 6 hour forecast. So, but the whole community appreciate this work, means this type of problem can be used in the future, and that's the reason people are doing work in this field and found a great success in this area. So definitely this particular scheme have a various drawbacks, and it did not consider the physical consistency. So that's the reason people did not believe in this technique, and then try to use the optimum interpolation. So optimum interpolation is a very simple example which told that if my analysis equations XA can be written as a XB plus a weight W X observation minus XV. And if we will take the subtraction of minus XT in both sides, subtract XT in left hand side as well as in the right hand side, what will happen? XA minus XT can be represented as a error in my analysis. XP minus XT can be represented as a error in my background, and X OBS minus XT can be represented as error in my observations. So my error equations can be written as a epsilon A equal to epsilon B plus weighting function W epsilon OBS minus epsilon B. So that's the term, means the actual equation can be write as the equation in the error terms. So if we will take the ensemble average of this, so what we will get? We will get a ensemble average of epsilon A, epsilon B, as well as the rest of the term. And now the first and foremost constraint which we put in optimum interpolation technique is that my error distribution is unbiased. Unbiased means my EV as well as E observation both are 0. So if my both the error, means error in my background and error and in my observation are unbiased, so based on these equations, what we got that error in my analysis is also unbiased. Now again, if we will take the square of this equations, and what we will get that here, we will get a weighting function W here when we optimize these equations, and this the weighting function W is just based on the error in my background and error in my observations. So this is a unique thing which used throughout the data assimilation technique, that based on the error in my observations and error in my background, we can find out, we can tune my analysis which is best fit to the true state of the atmosphere. So if we will give just an example, if we will give large weight to the larger weight to the background error, what will happen? My analysis will be shifted towards the background. And if we will get more weight to the observations, what will happen? My analysis will shift towards the observations. So based on this, if we will use this in the form of a multidimensional, here n is my degree of freedom. So what we got here, the extension of this in multivariate cases, XA equal to XB, and K is here weight matrix, which we will call as a Kalman gain in my next few slides. And Z is my observation vector, and H is my observation operator, and XB is a previous state from the atmosphere. And here the K is can be written as a B, which is known as a background error, the error in the background term. H is my operator, it's a transform of the H operator, and R is the error in my observation. So now if we will consider this equation is a n cross n matrix. B is a n cross n matrix. And now n is my 10 to the power 9. So now we have a matrix of 10 to the power 9 into 10 to the power 9, and I want to calculate the inverse of this big matrix. So that type of problem came in this data assimilation technique, and various substitution mathematical equations are used to solve this kind of problems. So again, there are few remarks on the optimum interpolation type of technique, that calculating this Kalman gain, which required the inverse of a very huge matrix, is not feasible. So, and again, whenever the operators are highly nonlinear, like radiated transfer model for the satellite observations, this type of techniques are not very useful. Again, because here we required a inverse of a very big matrix. So what we did, in place of running the whole global model, we divide our global domain to a small blocks. And due to this block, what happened when we join all the blocks together, there are some kind of jumps, which we normally called as a unstable conditions. So then there are some mathematical theory which told that if we have a linear space, and with this we also have a linear as well as unbiased state of the atmosphere, the least square solutions based on the Gauss-Markov theorem is the best solution from all possible solutions. So this is the basic assumptions of the optimum interpolation type of technique. Means we required a linear estimation theory, unbiased errors, and then only the least square solution, the optimum solution, is the best solution. But the constraint is here that this is valid for all the linear spaces. Whereas in the variational method, which we are going to discuss now, if with linear space, we also have a Gaussian space also. Means now here we have three more conditions, three constraints. One is the linear constraint, another is the unbiased, and then Gaussian also. So what it told that the least square solution is the best solution, not only for the linear space, for non-linear space also. And that is based on the Rao-Blackwell theorem, and it's a CNR Rao, sir. So now variational technique is advancement of the optimum interpolations in terms of because here we can handle the linear as well as non-linear observation operator, and that is the biggest success of the community here. So then this variational method got a very big success, because here we can handle all kind of observations available from satellite, from radar, ground radar, from space-based radar, and various ground observations also. And that's the reason this technique is made as a operational technique in almost all the center worldwide. Either it's a ECMWF center from the Europe, or NCEP center from the USA, or from the Indian center like NCMRWF, IMD, Indian Meteorological Department, China. Everywhere this technique is made operational. So now we will go just a brief about the variational assimilation method. So again, the whole theory is based on the calculus of variation, which we normally study in our post-graduation. So what we did here, the objective is that we want to find out the optimal state of the atmosphere, and this state of the optimal state we will get from the iterative solution of a prescribed cost function. So here we will going to define a cost function, and then we will try to solve this cost function and find out the optimal estimate of the atmosphere. So now we consider that we have a two different information. One is the background and another is the observation. And we assume that both are the following the Gaussian distribution. So we can write the distribution of background Pxy as well as for the observation Pyx. So both are following the Gaussian distributions, and we assume that the distribution of observations and distribution of background both are mutually exclusive. So mutually exclusive means the total probability will be the our multiplications of these two different distributions. And once we will take the multiplication of these two terms and take the maximum likelihood estimation of this term, what we will we got a cost function defined as Jx equal to this much, 1/2 x minus xv. X is my here analysis state which we want to calculate. xv is my background which is available from my earlier forecast. B is my error in my background. So this is called as a background error covariance matrix. Then Y is my observation. H is a operator. H is a operator. It may be an interpolation operator because within a grid, maybe my observation location are not situated at the model grid. So it may be an interpolator operator, or maybe it's a forward model, like from the basic meteorological parameter to the satellite radiances or reflectivity. And again, R is the error in my observation Y. So, and this R is called as a observation error covariance matrix. So now the objective is here that I want to minimize this cost function with respect to X and consider this as a equal to 0. And what we got here, that B inverse X minus XP can be write as a S transpose R inverse Y minus HX. It's a very simple mathematics. And what we received here, that the analysis X can be write in terms of this term S transpose R inverse Y minus HXP. And again, now we reach a statement that B, which is a matrix of a 10 power 9 into 10 to power 9, we want to calculate the inverse of this big matrix. So now again, the beauty of mathematics came. If I give you just a brief history of this Sermon-Morrison-Watson inversion formula, actually at that time, this type of inverse formula, various inverse formula exists in the theory, and no one think that this much huge application will be in the future of this particular inversion formula. And the biggest advantage of this term is that in this first state, we are deriving the inverse of a very big matrix, which is a 10 to the power 9 by 10 to the power 9. But after using this inversion, my matrix is converted as a inverse of R plus HBS transpose. So the dimension of this R is very less as compared to the dimension of my background. So that's the biggest advantage, and this final matrix is used throughout the world now. So there are various advantages of the variational method, and when we call this as a three-dimensional variational method, the term 3D represent here that we have a three-dimensional, one in the X direction longitudes, Y direction latitudes, and Z direction is for the altitudes. The issue with this equation is that we are not considering the time. So that is the beauty of the next scheme, which told that not only these three dimensions, we will consider the time dimension also, so that so in 3D bar type of technique, what we assume that whatever observations are available within a time window, we consider that they are valid at the same time only. Whereas in 4D VAR, we are assimilating, we are use the data assimilation at the correct time, at the time of the observations. So this is the beauty of 4D VAR type of technique, and the whole 3D VAR methods are extended for the fourth dimensional of the time. So with this, we've got a very beautiful conditions here, that because when we are using the observation at the correct time, we are following the trajectory of the models. As the model goes in the time, we have observations, and we put the observation at the precise condition. And with this, it's also use the model dynamics, because models are running in the forward, and then we assimilated the observation at that time, and then we are correcting the model trajectory. So that is the reason, sorry, so, and that is the reason this scheme become a very popular technique. So there are two techniques which we are using most of the places. Either it's a 3D bar type of technique or 4D bar type of technique, which where the fourth dimensional is a time. So again, based on the fourth dimensional, the cost function is slightly modified. Now my cost function is also based on the summations of t equal to 1 to n, where in place of simply y, we have a yt, where the observation with respect to time. So that is the advantage of this 4D VAR type of technique. So till now, whatever technique we discuss, we are using the, assuming that the error in the background, error in the first guess are fixed. It's not vary with the time. So that is the big disadvantage of the variational method as well as of the earlier optimum interpolation method. So then the theory of the weak constant for DVAR and the various other theories came and told that the error in the background term also should be the based on the flow dependence. So based on this, if we will consider the standard cost function for the full atmospheric problem, we consider that we have a different terms. One term is based on the my first guess background, and here error is my P0, P0. Next term is based on the observations, and error is my observation error covariance matrix, and the third term is based on the model error, because till now we did not consider that model also have a error, and that also should be considered for the modeling. So that's the reason people think that why not model error should also be considered. So
Sir, sorry to
so
interrupt
with
you.
this, yes,
Sir, we have 5 minutes more.
okay.
Oh.
Okay, so with this, we have a various drawbacks of the these technique, optimum interpolation, 3D VAR, 4D VAR type of techniques. And then with the help of the Kalman filter, we are making use of the Kalman filter and find out that background error can also be propagated with respect to the time. So this is just a example of Kalman filter, which told that how the background error in the model can be used for the propagation of the error. And that's the reason in most of the places people are using the variational method, either 3D VAR type of technique or 4D VAR type of technique with the Kalman filter type of technique, which is very expensive, computationally expensive. So those type of techniques are used worldwide for the operational implementation. So with this, okay, so I will go you. So there are various difficulties, non-linearities in this field. And definitely the use of the model error with time is a very big challenge. Definitely we have a very different efficient data assimilation technique, and we generate a various kind of ensembles to predict the weather system. And right now people are much more focused about the various machine learning technique to resolve the complications of the model physics. And with this there are various type of target sensitivity experiment, that what kind of future sensors are required, and how we can improve a particular weather conditions. So with this I want to complete here. Thank you very much.
Yeah, thank you very much, sir. Ma'am, is there any question from your end?
I have one question, sir. Sir, in optimal estimates, you use the W,
Yes,
optimal interpolation. Uh, how you calculated this W? To
yes,
my
yes.
knowledge, W is the weight. Am I right? So how you
W we
calculated this
calculate based
value?
on the observation error, background error terms. So based on the observation error and background error, we optimally optimize the cost function, and then we calculate the W.
Okay, and somewhere we had the J
Yes,
function, J subscript. Is this J
yes,
matrix?
it's a cost function which we defined here as a, and this is a big matrix. So, but here we consider this as a quadratic function.
Okay, okay, so we can minimize the error.
Yes, yes.
Is this the purpose for having quadratic function?
Sorry.
Error can be error can be minimized if we go with quadratic function. Is that the criteria which you are using?
Yes, actually, the issue is that if we will take a quadratic function, the minimization is little bit easier. But if we will take a higher order term, then maybe in some cases we will not get the minimal conditions.
Yeah, even degree order will increase, so may not be easy to work with. Okay,
Yes,
very good, sir. Very good application in meteorology. But I still have one question: why our forecasting department is not able to forecast correctly?
actually, the issue is not that. Even the worldwide, the biggest center of the world, like ECMWF from Europe or from the NCEP from the USA, they are also not able to give the very precise weather condition over the our region. The issue is that weather forecasting over the tropical regions are based on the two system. One is the advection and another is the convection. And here convection is very unique property. Whereas over the mid latitude and other region, the weather system are based on only advections. Advection means if we will know the temperature and moisture condition very precisely, we will get how it will advect. So means modeling of the advection equation is very precise. Whereas the modeling of the convective system, because we have a, here we have a both the conditions, convection as well as advection. So modeling of convective system, again it is based on the nonlinear hyperbolic equations. So the solution of those type of equations are very complicated. So that's the reason the prediction in general over the tropics are very difficult, and worldwide people need this region as a test bed.
Okay, yeah. Now I came to know that we have two different systems, and that is making it complicated to predict.
Yes.
Thank you. Thank you. Let us see if there are any questions from the audience. No, no questions from the Facebook Live. Thank you. Thank you, Prashantji.
Thank you, ma'am. Thank you, everyone.
Thank you very much, sir, for your interesting talk on numerical weather prediction. Our next speaker is now connected with us. So I request Mr. Pratik to introduce our next speaker.
Thank you, Milan. Now we are going towards the end of this session. I would like to introduce to you to Professor Gaurav Dwivedi. Professor Gaurav is currently working as an assistant professor in the Department of Mathematics at Birla Institute of Technology and Science, Pilani campus since 2018. He was awarded Science and Engineering Research Board India Postdoctoral Fellowship. He has also visited abroad for academic training funded by IIT Gandhinagar and for attending international conferences. He did his MSc from Indian Institute of Technology, Delhi, and received his PhD in mathematical science from Indian Institute of Technology, Gandhinagar. His principal research interest is in the analysis of elliptic partial differential equations. His research work has been published in many reputed national and international journals like Differential Equations and Applications, Mediterranean Journal of Mathematics, Journal of Mathematical Analysis and Applications, etc. He has excellent research contribution in terms of research publications in Journal of High Repute, uh, handling externally funded or sponsored research project as principal investigator sanctioned by SERB under mathematical research impact centric support known as matrix. He has successfully completed institute sponsored research projects under research initiation grant. I am now inviting Professor Gaurav to deliver the talk on biharmonic equation with exponential nonlinearity on the Heisenberg group. Over to you, sir.
Thank you, Pratik, for a nice introduction. Uh, I would like to thank Professor Shah, Dr. Akansha, and Department of Mathematics at Gujarat University for having me here. Uh, Today's talk is on biharmonic equation with exponential nonlinearity on the Heisenberg groups. So in this, we are going to see existence result for a biharmonic equation where nonlinearity will grow exponentially. So I'll try to keep this talk as elementary as possible, and we'll try to define most of the terms. So the idea would be as follows. First, we would see how biharmonic equations came into picture in Euclidean domains. Then we are going to see few results for biharmonic equation or Laplace equation with exponential nonlinearity in bounded domains of Rn, and then we'll gradually move to the Heisenberg groups. So this equation, Laplacian square u is equals to x. So Laplacian is the usual Laplace operator, as del square u over del xi square, sum it for uh, I is equals to 1 to n, where n is the dimension of the space. You take its square, that's called bilaplacian. So we are interested in this type of problem where omega is a subset of Rn. It can be bounded, unbounded, or it can be entire Rn as well. For today's talk, we are going to consider only bounded domains. And if your domain has boundary, then we can have some boundary conditions. And then we can talk about under what conditions on this function f we may have existence of solution. So in general, this f can be non-linear as well. So linear case is pretty much straightforward. We will focus on non-linear function f. Now this equation first came into picture in explanation of something called Chladni figures. So Ernest Chladni, he was a German physicist and musician. So once upon a time, he was on a beach. He had a metal plate along with a violin bow. So there was some sand on the plate, and he started making some vibration on the plate. Then, depending on the frequency of the vibration, different sort of figures were formed. So as you change frequency, the shape of figures are going to change. So this was considered an interesting problem at that time. So the Napoleon was very interested in this problem. So how to form a mathematical model which explains formation of these diagrams. So he proposed a cash prize for a mathematician who can solve it. So Sophie Germain was the first person who came up with a model to explain these diagrams, and then later that model was improved by Kirchhoff and all. And Finally, it was shown that these figures are related to eigenfunctions of biharmonic equation with Dirichlet conditions. Another famous application of this came as an explanation of this Tacoma-Narrows suspension bridge collapse. So this was a suspension bridge built in Washington, and it collapsed within 10 months of its inauguration in around 1940. So there were various mathematical models that were used to explain why this actually happened, and few models contained fourth order equations, to be precise biharmonic equation, in their explanations. There are several explanations for this phenomena. You can find papers as late as 2015 where they are still trying to give a model which can describe this phenomena. Now there are several other applications of biharmonic equations as well, such as in radar imaging, MEMS, epitaxial growth, etc. But in today's talk, we are just focusing on the theory of a biharmonic equation. That means under what conditions we can have existence of solution. So before I go ahead, I'll just define few basic terms which I'm going to use today. One such is the Palais-Semel condition. So suppose we have a Banach space X, and then we have a continuous functional J from X to R, and it's differentiable. Then we say that J satisfies PS condition if you can find a sequence UN such that JUN converges to C and J prime UN converges to 0. If there exists a sequence satisfying these two conditions, then there must exist a convergent subsequence of UN. So if J satisfies this condition, then we say that J satisfies Palais-Semel condition. Next is a famous result from functional analysis called mountain pass theorem. So the statement is given here. So we have a C1 functional which satisfies Palais-Semel condition, and there are two geometric conditions which are satisfied. So we have 2 points U0 and U1 in our Banach space X which are at a distance more than R. Then for all the points which lie on this circle, mod v norm v minus U0 equals to R, this condition is satisfied, then J admits a critical value which is characterized by this. Now this theorem gives us existence of a critical value. So we will try to relate our PDEs with critical points of certain functionals, and then this theorem can be applied to obtain existence of critical points, and then if we can show that critical points of the functional are actual solution of our problem, then our job will be done. Now I'll just explain the geometrical meaning behind this theorem and from where this name mountain pass comes. So suppose you have a mountain range in between two valleys, and there are 2 points U0 and U1 which were there in the statement. So these flags denote those points U0 and U1. Then you consider all the paths connecting U0 and U1, and let us say J denotes the height at each point. So JU0 is height at U0, JU1 is height at U1. Then you consider all the paths which connect U0 to U1, and then you choose a path from which you can reach from U0 to U1 in which you have to climb the least. So you choose infimum over all such paths, and that was the precise statement here. So J gamma t is collection of all paths joining U0 and U1, and then you are finally taking infimum. So this is the theorem which will give us existence of a critical point, which will in turn be our solution to the given differential equation. Next, we define a weak derivative for a locally integrable function. So I guess this has been defined yesterday, so I'll just quickly browse over it. So you have a locally integrable function u. So if there exists a function v such that this identity is satisfied, then we say that v is the weak derivative of u. So essentially what we do is apply integration by parts here. So if you recall, in integration by part, derivatives are thrown from one function to other. So as you keep integrating it, the derivatives on phi are going to decrease, and the same order of the derivative will come over u. And there will be some boundary terms which will vanish because phi belongs to CCM, which are functions which are 0 on the boundary of omega. So this is how we define weak derivatives. Once we have weak derivatives with us, we can define Sobolev spaces. So basically, these are subspaces of LP for which a weak derivative exists and they belong in LP. So we define Sobolev space of order k as set of all LP functions for which kth order weak derivative or all the derivatives up to order k are in LP. So this is how we define WKP. So these are defined for every value of p between 1 and infinity. The norms on these spaces are given by this. So this essentially is sum of norms of d alpha u. So we know that each of d alpha u is in LP. So we just take sum of all LP norms and power 1 by p. And these spaces are Banach spaces for every p. Next, we consider a subspace of WKP that we denote by W0KP. This is closure of CC infinity omega in WKP norm. So for smooth domains, W0KP is a subspace of WKP of all those functions which are 0 on the boundary, if you consider the first order Sobolev space, and then if you consider higher order Sobolev space, then u along with its derivative, they are 0 on the boundary. So this is the space in which we will be interested in. Then there is another notation which we are going to use is H0k and HK. These are nothing but WK and W0k for specific value of P that is equals to 2. So we know that LP space becomes a Hilbert space for phi is equals to 2. That is why we are interested in specific value of P that is equals to 2. And for that, the standard notation is HK or H0k. And there are norms defined on these spaces. Then there are some embedding results for WKP. So the first result says that if n is bigger than Kp, then WKP is embedded in LQ omega continuously. So that means the inclusion map from WKP to LQ is continuous, provided Q lies in this range. Now, as you see from here, this exponent NP over n minus Kp, this becomes infinity at n is equals to Kp. So for n is equals to Kp, we have this result. WKP omega is embedded in LQ omega, where Q is bigger than equals to P and smaller than infinity. In next slide, we are going to see that WKP omega is embedded in LQ for all Q smaller than infinity, but this is not embedded in L infinity. So we have examples of functions which belong to WKP but do not belong to L infinity omega. So inclusion in L infinity is not there. So we have to remain strictly smaller than infinity. And then for n less than Kp, we have this embedding. WKP is embedded in space of Holder continuous functions C0 alpha. So for today's talk, we will mainly focus on this second case when n is equals to Kp. Just keep this in mind. WKP is embedded in LQ for all Q smaller than infinity, but it is not embedded in L infinity. Now, if we have bounded domain, then all the embedding results which I have shown here, they will also be true for the subspace W0KP. So if you replace WKP by W0KP, then again all the embeddings will remain true as it is. And these embeddings are compact as well. So compact means the inclusion map that you are taking from WKP to LQ, that inclusion map is compact. So all the embeddings will be compact except for the first case, the WKP will be compactly embedded in LQ for Q strictly smaller than this exponent NP over n minus Kp. So embedding of WKP in this exponent is not compact, but any exponent is strictly smaller than this, the embedding is going to be compact. So here is an example when n is Kp, WKP is not embedded in L infinity. For k is equals to 1, I have written an example. So if you're interested, you can verify that this function belongs to W0n omega, but this does not belong to L infinity omega. Now, Let us quickly define what a weak solution would be. So this is the sort of problem in which we are going to be interested in. Laplacian square u is equals to gxu in omega. Omega is smooth and bounded domain in Rn. And u as well as normal derivative of u, they are zero on the boundary of omega. So this boundary condition is called Dirichlet boundary condition. To find out weak solution, we multiply this by a test function in space h02 and then use integration by parts. So on integrating, we get this integral over omega. All the boundary terms are going to vanish because we are working in h02 space. So u and its normal derivative is zero on the boundary. So that will make boundary terms go away. So any function u satisfying this second equation is called a weak solution. So these are the solution in which we are interested. Now, it can be shown that weak solution of the problem, that means the solutions u which satisfy this equation, they are nothing but the critical point given by this functional. So this again is not a very difficult result to prove. It is more or less easy to show that critical points of this functional are the weak solution. So now our aim is going to be just to show existence of the critical points for this functional, because once we are able to show that, our problem is going to have weak solution. Now this capital G here is integral of the small g. Small g occurs on the right hand side of the given equation. Now suppose our G has this type of growth condition. It grows like some constant times mod s raised to p minus 1. So this is a small g. If you compute capital G from here, that was the integral of small g with respect to the second variable s, then it will grow like mod of s raised to p. So in the integral, we are going to have a term integral mod of s raised to p. So for the functional to be well defined, that value should be finite. And there the embedding result will help us, because in the embedding result, we know that WKP is embedded in LQ for certain values of Q. So this will be the critical exponent in our case. So if you recall, it was NP over N minus KP. P here is 2. So it is 2n divided by N minus K is 2, because we are working with second order Sobolev space. So 2 multiplied by 2 gives us 4. So whenever we choose P smaller than equals to 2n over N minus 4, our functional is well defined, and we can prove existence of solution using mountain pass theorem. So that I'm
Hello, Gaurav sir. He seems to have a net problem because he got freeze. Akanksha, please check with Gaurav. Yeah, he might be rejoining.
Yes. All participants are requested to please stay connected with us. Sir is having some internet issue at his end and he's trying to fix it. So please be connected. Sir is trying to reconnect with us, so please keep patience for some time.
Okay, am I audible?
Yes, sir, you are audible.
Okay. Okay. So at what point did I lose connection? So I don't know. Actually.
Slide
Was
number
this
6.
okay? Okay. So this was a singular version of Moser-Tudinger inequality. So
Dr. Gaurav, please share
yes,
your screen. Please share your
yeah.
screen.
Okay. Is it visible now?
Yes, sir, it
Yes, sir.
is.
Okay.
Yes, sir. Please go ahead.
Yes, sir.
Okay. So this is a singular version of Moser-Tudinger inequality. So if you recall the standard inequality that had the term mod u raised to n over n minus 1, but this term in the denominator was not there. So it was proved by Adimurthy and Sandeep that this integral will also be finite if you choose beta to be between 0 and n. Now we can also prove that the supremum is going to be infinity whenever we choose a constant alpha which does not satisfy this condition. So this supremum is only finite if alpha satisfies this condition. So if we choose beta is equals to 0 in particular, so we will go back to the standard Moser-Tudinger inequality. Beta is equals to 0 just gives us this term, and here we get alpha less than equals to alpha n, which was the statement of the previous theorem. Now, as it is clear from here, this inequality will help us in establishing the existence results for the singular problems, which look like fxu divided by mod x raised to a, where a will be less than n, and we assume that f satisfies the standard exponential growth condition. So using the similar techniques and with the help of this singular version of the inequality, the existence result was proved by Adimurthy and Sandeep in the same paper. Now, all the inequalities that we have discussed so far, they correspond to the first order spaces. The inequalities can be generalized to the higher order for the higher order derivatives as well. So this is called Adams inequality. So this inequality holds when u belongs to the general Sobolev space WKP. So the earlier results were for W0n, now W01n. Now we have the results for the higher order Sobolev spaces W0KP. And the same uh, type of result is true, that exponential of beta mod u raised to n over n minus k, this value is going to be finite. Uh, Corresponding to the singular version in the first order case, we have a singular version uh, of the inequality here. That was proved by Lam and Lu in 2012. So they established that this supremum is finite whenever beta is smaller than this constant beta alpha n k, and whenever we choose beta bigger than this constant, this supremum becomes infinity. So now both of these inequalities help us to establish existence results for higher order problems when the nonlinearity has exponential growth in them. So this problem, existence result for this problem was established by Lam and Lu using the standard mountain pass theorem technique and Adams inequality. So the growth conditions that they assumed were this. So there are two types of conditions. First one is mod of fxu divided by exponential alpha u square. This is 0 as mod u goes to infinity for alpha bigger than alpha naught, and this is infinity whenever you choose alpha smaller than alpha naught. This is called critical exponential growth condition, because here if you want a function f to satisfy this condition, f should have form of exponential of, let us say, some constant a beta u square. Then when you'll take this into the numerator, you are going to get beta minus alpha u square. Then for some values of beta, it will be 0. And then for some other values of beta, it will be infinity. The other condition is subcritical exponential growth. This condition says that fxu divided by exponential of alpha u square, this is 0. And it has to be true for all alpha bigger than 0. So if you want to have an example of a function which satisfies this type of condition, that will be of the form u raised to p for any p. So you have some polynomial power in the numerator, exponential power in the denominator. As u goes to infinity, this will go to 0 for every alpha positive. If you have exponential growth in the numerator, then this limit will not be 0 for every alpha. For some alpha, it might be 0. And for some alphas, it might not be 0. So that was the second case. And that sort of growth is called critical exponential growth. Okay, now we just discuss brief details about the Heisenberg group, and then we are going to discuss the Adams inequality, which on the Heisenberg group, which we have established. So Heisenberg group is R2n plus 1. So this is 2n plus 1 dimensional Euclidean space, but the product is defined in a different manner. The product is defined like this. So take two elements, x, y, t. X and y are in Rn. T is a real number. Similarly, x dash, y dash, comma t dash. Their product is defined as x plus x dash, y plus y dash, t plus t dash, and this quantity. Now, due to presence of this quantity here, this product is going to be non-commutative. So under this operation, this forms a non-commutative group. Now we will consider the domains in this Heisenberg group Hn, and the measure is going to remain the same Lebesgue measure in the Euclidean space R of 2n plus 1. This Hn along with this operation also forms a Lie group. Its Lie algebra is generated by these three vector fields, and the Lie bracket is given by the standard way. So bracket of AB is nothing but AB minus BA. So in that way, if we define bracket, this will form a Lie group. Lie algebra is generated by these elements. So the standard notation that we are going to follow for any element of Hn will be this. So it will be denoted by z comma t. T will be a real number and z will be an element in R2n. So you can also consider z as an element of Cn. So mod of xi is given by this formula. So this is nothing but distance of xi from 0. Mod z is to 4 plus t square is to 1 by 4. This number 2n plus 2 is called a homogeneous dimension of this group Hn. So this is another fact which we are going to use. So next thing that we'll discuss is what is Laplace operator on this group. So usual Laplace operator is del square over del xi square. You sum it from I is equals to 1 to n. On Heisenberg group, gradient is defined as this quantity x1, x2, xn, y1, y2, yn, which were the vector field which generated the corresponding Lie algebra. And Laplacian is defined as sum of xi square plus yi square. So if you plug the values of xi and yi here, you are going to get this expression. So this is how you define Laplacian. And similarly, you can take its square. So you can compose Laplacian with Laplacian to get its square, and you are going to get a biharmonic operator on the Heisenberg group. So we can define the Sobolev spaces in similar manner. The notation that we are going to use for Sobolev spaces in Heisenberg group are D1P and D01P. So these are all the spaces where where function is in LP and all its first order derivative are in LP, and D01P will be the subspace of D1P such that U is 0 on the boundary. Similarly, we can define the higher order spaces on this Heisenberg group. So now, since Laplacian is well defined in the measure, we are just taking the Lebesgue measure in R2n plus 1. So all these integrals are defined in the usual manner. Here are the embedding theorems. So these are analog of the embedding theorem in the Rn case. So only thing that has changed now is in place of n we have q. This q is the homogeneous dimension, which is 2n plus 2 for hn. So d0 kp is embedded in lp star, where p star this is pq over q minus kp. So we have just replaced n by q and we have the similar embedding results. And again, we are just going to focus on the second result because we are concerned with exponential growth. So we will be working in the case q is equals to kp. So we know that it is embedded in lr omega for every r less than infinity, but it is not embedded in L infinity omega. So the analog of Moser-Tudinger inequality for Laplacian was proved by Kohn and Lu. So if you observe, this expression is similar to the expression in the Rn case. So there we had alpha n mod u raised to p over p minus 1. So this q prime denotes the same thing, q over q minus 1. And this value will be finite if alpha is less than equals to alpha q, and if we choose a constant which is bigger than alpha q, the supremum is going to be infinite. So once the inequality is established, you can study the corresponding equation. And we also have the singular version of Moser-Tudinger inequality. So the numerator is the same thing. In the denominator, we have rho xi raised to beta. Rho xi was nothing but mod of xi, the distance of xi from the 0 with respect to the norm on this hn. So once we have this singular case of the inequality, we can establish existence results for these type of problems. F xi u divided by rho xi raised to beta. This side here is generalization of Laplace's operator. So if you just choose a xi, and let's say the second variable is eta, if you choose a xi eta to be just eta, then divergence of grad u will be the Laplacian. So this here generalizes the Laplace operator. Then it was proved that for small values of h, this problem admits a weak solution and so on using the variational techniques and the Moser-Tudinger type inequality. Now, the Adams inequality in the case of Heisenberg group was open. So we tried to prove Adams inequality for singular as well as non-singular case, and we came up with this result. So we so far have established this result for H1. So we are in Heisenberg group Hn, and we are considering a particular case n is equals to 1. So Q will be 4, that will be the homogeneous dimension. And in that case, we will have a result which is similar to the Adams inequality in Rn. So this inequality and this here is the singular analog of this Adams type inequality on the Heisenberg group. So rho xi again is the mod xi, which is distance of xi from the point 0. So if we choose a suitable constant, then this supremum will be the supremum over all u for this integral will be finite, and after that constant, the supremum is going to be infinity. So I'll skip the ideas behind the proof. So it essentially uses this fact that if you can write your function u as convolute as I2 star f, this is called a Rees potential. So if we can express u in this form, then we can make use of this result to show that this integral is constant, and then it can be further utilized to show that we get the required result. After proving these inequalities, we established the existence result for these type of problems, f of xi u over rho xi raised to a, where f satisfies the usual critical and subcritical exponential growth conditions. Now, in all the results thus far, the singular version of the inequality, whether it was Moser-Turinger type or Adams type inequality, was used to establish existence result when a was strictly smaller than q, because the inequality is only valid when a is smaller than q. But we also used a iteration technique to prove the result for a is equals to q as well. So the case a smaller than q is directly handled by the Adams type inequality, which we have established, and the mountain pass theorem. So to verify the geometric conditions which were required in the mountain pass theorem, we have the following lemma, that there exists a rho positive such that for which Ju will be positive on this is fair. So there we had 2 points, u0 and u1. We are taking one of that point to be 0, and then we have the second condition that will be satisfied by this lemma. So we can show that Palaisa-Smil condition is satisfied at every level C. So when f has subcritical growth, PS conditions are satisfied for every C in R. But in case of critical growth, PS conditions are satisfied only in some interval, and then we try to make use of PS condition in that interval to establish existence of solution. So if PS conditions are satisfied at every level, then we can directly apply mountain pass theorem, but otherwise we'll have to work a little more. So for the critical case, when the power was exactly equals to q, we consider the truncated problem q minus 1 by n. Now this number q minus 1 is smaller than q. So for each n, this problem can be solved using the previous techniques. So we get a sequence of solutions un, and then we finally show that the sequence that we have obtained is convergent, and limit of that is the solution to our problem. So to solve this problem in the power q case, we first reduce into a subcritical problem, and then from there we try to get a sequence which actually converges to the solution of the real problem. So I'll end my presentation here. So these are the results which we have proved. Right now, the results which are still open are, first of all, this Adams inequality we have proved only for n is equals to 1. So for general n, that is one thing that can be looked into. The other thing is that we can do is, right now we have these results only in the bounded domains of Rn. So what we can do is try to look whether, bounded domains of Hn. What we can do is try to look at whether these results can be extended to entire Hn or not. So with this, I'll stop. Let me know if any questions are there. Thank you.
Thank you very much, sir, for your talk. Any question from your side, ma'am?
Yeah.
Gaurav sir,
Okay.
you can switch on your video.
Yeah.
No, I don't have a question because it was so lucid that if one has paid attention in the first slide, he can reach to 66th slide. So,
Okay.
thank you for a lucid presentation.
Thank you.
Let's see if there are any questions in chat box. There are no questions from the chat box. That says your lecture. In fact, everybody is saying that very nice informative session and informative lecture, simple and lucid lecture. So thank you very much on behalf of Department of Mathematics, Gujarat University.
Thank you, ma'am.
Srivastava. Thank you.
Thank you.
Over to you, Milan sir.
Oh, thank you, ma'am. Thank you very much, Gaurav sir. A lot of participants are asking about the feedback form. So please note that the link for the feedback form will be sent to your mail ID, which you have provided at the time of registration. The link will open till tomorrow, that is 28th September, up to 12 noon as per the Indian Standard Time. So all of you are requested to fill that form correctly, because that name is going to appear in your certificate. And after filling the feedback form, that process will take up to 1 week to get the certificate. So please keep patience for some days. So now I request Mr. Pratik to please conclude the session.
Thank you, Milan. So, concluding the event on behalf of Department of Mathematics, Gujarat University, I am thankful to all the participants for your active participation and cooperation. Also, I am thankful to all the speakers for giving their valuable time and sharing their knowledge with us. I'm sure, being an academician, we all are looking forward for such occasions and events which energize our intellect and build an optimistic relationship with each other. Let's grow and learn together. Stay safe, stay healthy. Have a great day. Thank you once again.
Thank you, all of you.